Greetings, Brian here. Now last week we talked about motion in one dimension, and we're going to take that and we're going to extend that to motion in two dimensions. But as it turns out, motion in two dimensions is just two one-dimensional motions that happen at the same time. So everything that we've learned applies, and it's just the combination that's new this week. Now remember, we looked at uniform motion, that is motion with constant velocity. And for motion with constant velocity, the position just steadily changes with time, okay? And the slope of the graph that we've drawn right here is the velocity, and we can use this relationship to calculate positions. We also looked at motion with constant acceleration, and we had three relationships for that, which we've used to solve problems. And in this case, the velocity is steadily increasing. The position graph would look more like a parabola because it's having a steadily changing slope. And one particular type of one-dimensional motion we had, of motion with constant acceleration, was free fall. And the key thing about free fall is the acceleration was just equal to negative 9.8 meters per second squared. So it was just motion with constant acceleration, but it had a very particular acceleration, and you have that acceleration if an object is going up or coming down. Now I want to do a quick review of trigonometry, and this is something we talked about in the very first week of class. Remember, if I have this triangle right here, we have relationships for sine and cosine and tangent that are ratios of the sides, or if I know the sides, I can find the angles by doing the inverse trigonometric functions. And this is something that you've learned about previously before taking this course. Now let me, in 1 minute, just talk about how we are going to use trig as a rule in this class. If I take my trig functions from the previous slide and I rewrite them, I can say this. A, which is the side of the triangle that is adjacent to the angle theta, is just equal to C, the hypotenuse, times the cosine of theta, because cosine is the one for adjacent sides. B, the side that is opposite the angle, is equal to C, the hypotenuse, times the sine of theta, because the sine of theta is for the opposite sides of the triangles. Now what I'm going to do is this. Instead of looking at just A and B and C and looking at triangles, I'm going to imagine we have a vector. And let's have a vector V here. That's a velocity vector, and it's headed basically in two directions. You can see there's a horizontal and a vertical component to that motion, and I can break that vector into two component vectors, Vy, the horizontal velocity, and Vy, the vertical motion. And that's typically what we're going to do with two-dimensional motion, is we're going to take the velocity vector, which has both horizontal and vertical pieces to it, and we're going to break it into those two components. And arguing based on what we've just written for the sides of the triangle, I can say this: Vx, that's the side that is adjacent to the angle theta. Vx is just equal to V times the cosine of theta. Vy, which is opposite the angle, is just going to be equal to V times the sine of theta. And as a rule, that is what we're going to use trig for. And it is worthwhile to memorize this. Go ahead and commit this to memory and get good at this so that you don't have to be using any kind of SOHCAHTOA or whatever mnemonics for it. Just know how to do this. And let's look at an example. So suppose we have a car going up a steep 10% grade at 15 meters per second. Two questions. What is the angle of the grade? And then how many meters does the car climb each second? Now quick strategizing. Okay, how many meters does the car climb each second? Well, the car climbs each second. That's just Vy. That's the meters per second of vertical motion. Angle of the grade is, I'm just looking for the angle theta. Now we're told that the 10% grade is the rise over the run of the road, okay? So if the road is like this, and it's a 10% grade, what that means is, okay, what that means is 10% is the rise over the run. So if I have a rise of 1, I have a run of 10, because the rise is going to be 10% of the run. So if I'm looking for the angle theta, we can use our trig functions, and I can say that theta is equal to the inverse tangent of 1/10. And that is just 5.7 degrees. Okay, so it's a 5.7 degree angle. Okay, and now what we're going to do next is this. First, let's clear the decks a little bit. Let's go ahead and erase what's here. Okay, we're going to get rid of that. And then we're going to draw the slope again, but this time I'm going to draw it using a velocity vector. The car is moving up the slope, and it's moving at a speed of 15 meters per second, but that velocity vector is tipped at an angle of 5.7 degrees to the horizontal. And I'm looking for Vy. That is the vertical component of the velocity. Okay? And so the vertical component of the velocity, Vy, is just going to be equal to the hypotenuse, i.e. the vector itself, 15 meters per second, times the sine of 5.7 degrees. Okay? That's what we get. And then if I compute what Vy is, I get 1.5 meters per second. And a quick assessment, that seems reasonable because it's 15 meters per second, it's at a 5.7 degree angle, almost flat, and the rise over run is 10%, so I'd expect the car's rising to be about 10% of its motion. So that makes sense. That's the type of thing we're going to be doing with vectors and angles. And here's our results. There's our angle, and there is our vertical speed. Now the first case of two-dimensional motion we're going to look at, and this is the first one that you see in Chapter 3, and by the way, I want you to start reading Chapter 3 in the textbook. In Chapter 3, we discuss motion on a ramp, and if I have an object sliding down a ramp, it is going to accelerate. The speed is going to change. The direction of the motion isn't going to change, but the speed will. And in principle, if you have something which is just acting under the influence of gravity, you just have the free fall acceleration. But the component of the free fall acceleration perpendicular to the ramp, you can't have that. The ramp blocks it. I only get the component parallel to the ramp, and the component parallel to the ramp is given by this relationship right here. And by the way, here's a simplification. It says plus or minus g times the sine of theta. That just says, is it going to the left or is it going to the right? Let's just do this. Anytime something slides down a ramp, it's going to go to the right. So the acceleration down the ramp is just g times the sine of theta. So again, it's a component. And we're going to take the x-axis to be along the ramp. And so we've taken a two-dimensional motion problem because it looks like the motion down the ramp is in two dimensions. We've just said, no. We're just going to take that and let that be our x-axis. And so in fact, it's going to be a one-dimensional motion. So our first two-dimensional motion problem, we just turned into a one-dimensional motion problem. Look at us. And here's a problem that uses this. A 120-meter ski ramp is inclined at 21 degrees. Question, what is the maximum possible acceleration of a skier moving down the ramp? And what is the maximum possible speed at the bottom? And we'll solve this problem the way we always do. We're going to start by strategizing. What type of motion do we have? And two, what are we solving for? Okay? Well, what type of motion we have is motion down a ramp. This is motion down a ramp. And what is the maximum possible acceleration down a ramp? Well, the ramp acceleration is just equal to g times the sine of theta. Theta is the angle with respect to the horizontal. And in fact, that's what the inclined at 21 degrees means. So theta is just equal to 21 degrees. And we're looking for the maximum speed at the bottom. This is motion down a ramp. We know the acceleration. The skier is going to accelerate down the ramp. So I'm going to have a skier up here at the top. Skier is going to accelerate down the ramp until the skier reaches the bottom of the ramp. The skier will be moving at a certain speed, and that is what we are solving for. Okay? That's our strategize. Next, let's do our preparation. We're going to first compute the acceleration for the skier, and then we're going to draw a visual overview as we always do with the important points and the values, reminding ourselves what type of motion it is and thinking about what equations apply. Well, the acceleration is just equal to g times the sine of theta. G is 9.8 meters per second squared. By the way, g is just a number. Okay, the free fall acceleration is negative g. It's negative 9.8 meters per second squared if we're looking in vertical motion. But in this case, I'm just using the number. The acceleration down the ramp is 9.8 meters per second squared times the sine of 21 degrees. And if I calculate that, I get 3.5 meters per second squared. And so the skier is accelerating down the ramp. Okay, skier starts out here. Skier ends up at the bottom of the ramp, moving at a certain speed. Okay, actually I'm going to draw that in the direction the skier is actually moving at a certain speed. That is my x-axis. And along the way, the skier is accelerating at 3.5 meters per second squared. Now let's list values. Okay, for the initial point, I'm going to take the x position is equal to 0. Okay. And actually, I don't care about times. I'm not going to worry about times and look at the velocities. The initial velocity is equal to 0. For the final point, the final position is equal to 120 meters because the ramp is 120 meters long. Okay, that's 120 meters. And the final velocity is, well, that's what we're looking for. Now this is motion with constant acceleration, and I want the relationship that doesn't use time, and so the relationship I'll use is just vf squared is equal to vi squared plus 2 times a times delta x. And with those things in hand, I can solve. I'm just looking for the maximum speed at the bottom of the ramp. I'm just looking for vf, okay? Looking for vf. Now we've made some assumptions. We've assumed you can ignore air resistance. And if I compute vf, I just take the numbers and put them in the equation. I'll let you do that. You end up with a final speed of 29 meters per second. Okay? 29 meters per second is like 65 miles per hour. That is speedy. That is speedy. So when we're doing our assessment, we can say, wow, that's intense. But it's a big ski jump. This particular ski jump is in Slovenia, a country that is near and dear to my heart. And people get going pretty fast when they go down that ramp. And then we're going to assess it. Does the answer make sense? Well, I said this is speedy, but in fact, people do get going pretty fast. And if you actually look at data for skiers coming off the end of this ski jump ramp, their actual speed is 28 meters per second, slightly less than the 29 meters per second that we calculated. But that makes sense because we've ignored friction, we've ignored air resistance. And so our final assessment is this does make sense in terms of our understanding about the way the world works. Now, the reason you go down a ski jump ramp is then you're going to go on some sort of path through the air, some sort of a parabolic trajectory. And that is a true two-dimensional motion because the skier is moving vertically. The skier is also moving horizontally. And so we have to look at motion in 2 dimensions and include both of them. And you can read about this so-called projectile motion in chapter 3. So I want you to read chapter 3 and read all about projectile motion. And the key thing is this. The horizontal motion and the vertical motion are independent, as we saw in class. So the horizontal motion continues at the exact same speed. The vertical motion is free fall. So the vertical velocity starts out with a certain value and it changes, and the change is just the free fall acceleration of 9.8 meters per second directed downward. And so we're going to take the projectile motion and we're going to treat it as 2 separate but related problems. The vertical motion, which is free fall, and the horizontal motion, which is motion with constant acceleration. And let's look at a first example. And we're going to look at something called dock jumping. And you can see this dog right here is running off the end of a dock. And they do these competitions where dogs run the length of a dock and then they jump from the end into the water. And you get prizes if your dog jumps the greatest distance. And most dogs start out with doing a flat jump. They just run off the end of the dock straight and as fast as they can. And if the dock has a height of 1.2 meters above the water, and that's a typical number, and a dog does a jump off the end of the dock, leaving it at 6 meters per second, and that is a typical number. Question, how far from the end of the dock will the dog splash down? We'll solve this as we always do by starting with strategizing. So first, we're going to say how we're going to model the motion of the dog, and there's two pieces. There's a horizontal motion and a vertical motion. And then question, how do we determine the time that the dog is in the air? And given that, what can we say about the horizontal motion? So here's what the motion will look like. So here's the dock, okay, and it's above the water. And the dog is running at 6 meters per second when it leaves the end of the dock, okay? And then the dog is going to follow a parabolic trajectory. But what we're going to do is we're going to treat two different phases of the motion. First off, I'm going to have horizontal motion, and the dog is moving at 6.0 meters per second. It will continue to move horizontally at 6.0 meters per second. But while it's moving horizontally, it's also undergoing free fall towards the water. So we're going to treat those two motions separately, but they are related because the dog is free falling, and once the dog has fallen a distance of 1.2 meters, it's at the water. And when the dog hits the water and we have splash down here, it stops moving horizontally. So we're going to figure out how much time it takes the dog to reach the water, how much time it takes the dog to fall by 1.2 meters. And during that time, the dog is going to be moving horizontally at 6 meters per second. So we can figure out how far from the dock the dog splashes down. Now we're going to do our preparation. Again, what are the important points of the motion? What are the values for distance, time? What equation we use to determine the time the dog spends in the air? What equation we'll use to determine how far the dog moves while in the air? Okay? Now, clearly the important points of the motion are when the dog leaves the dock and when the dog splashes down in the water, okay? So here's my dog, leaves the dock at 6.0 meters per second, and then sometime later, dog splashes down into the water. And when that happens, everything's over. Now, I'm going to write down variables for the position, but I'm interested in the x position and the y position, okay? So at the start, since the dock is 1.2 meters high, the initial x position we're going to take as 0, because that'll be for our horizontal motion, but the initial y position is 1.2 meters, okay? The initial time is 0. And the initial x velocity is 0. I'm sorry, the initial x velocity is 6.0 meters per second. The initial y velocity is 0. Now at the end of the problem, when the dog has splashed down, okay, let's just say, let's call this distance, let's call it d. That's how far the dog is from the dock when it splashes down. At the end, the x position is equal to d. The y position is equal to 0. The time is equal to, well, we don't know. And then the velocities, the x velocity is equal to 6.0 meters per second. It continued unabated. The y velocity, we don't know. But in fact, we don't need to know that. You're not asked to calculate how fast the dog is moving. We just want to know how far it moves. So what we're looking for is what is the value of this quantity d. And now we're ready to solve. All right, now we're going to solve this by looking at the vertical motion first, how much time elapses when the dog is in the air. And once we figure out the time, we can use that to calculate how far the dog moves. So let's look at the vertical motion. Well, the dog is in free fall, and it starts at an initial height of 1.2 meters because the dock is 1.2 meters above the water. It finishes at a height of 0 meters. The dog splashes down, and in between those 2 points, it's accelerating with an acceleration of negative 9.8 meters per second squared. Now, vertical motion under free fall is a type of motion with constant acceleration. And so I can use this basic relationship. I can say yf is equal to yi plus the initial velocity times the time interval plus 1/2 times the acceleration times the time interval squared. Okay? And for numbers, the initial position is 1.2 meters. The final position is 0. The initial velocity is 0. The dog is not moving vertically, so that term goes out of the equation. The vertical acceleration is negative 9.8 meters per second squared. And with that, I have everything in hand to be able to calculate what the time interval is. And for the time interval, I get 0.495 seconds, which for reporting my answer, I'm going to give to two significant figures, 0.49. And that's about half a second, and that seems reasonable based on the Spud Webb problem that we did. Spud Webb jumped to a height of about 1.1 meters, and he was in the air just a little bit less than half a second on his way up, so that seems about right. With the time in hand, we're going to calculate the horizontal motion. Now, the horizontal motion is uniform motion. So we can use this relationship. xf is equal to xi plus the velocity times the time interval. Well, the dog moves at a uniform horizontal speed of 6.0 meters per second. It does that for a time of 0.495 seconds. And I've used the full 3 sig figs there to eliminate any kind of rounding errors. My initial horizontal position is 0. The final position we called d. Okay, that's what we're looking for. We're looking for that value of d, the distance that the dog travels. And if I put in numbers and I round to two significant figures, I get the distance that the dog travels while it's in the air is 3.0 meters. So the dog is in the air for about half a second, during which it travels about 3 meters. Now, let's think about this. Okay, 3 meters. Of course, we always have to do an assessment. Does this answer make sense? 3 meters is approximately equal to 10 feet. And if a dog runs and jumps off a dock and ends up 10 meters from the end, that seems pretty good. They hold the dogs in place, and they don't let them do like an infinite run up. It's a short distance. They do a burst of speed, and if they land 10 feet out, that sounds pretty good. And I have seen my dog Milo do this, and he ends up about 10 feet out. That seems about consistent with my impression of the way the world works. So yes, this is a reasonable thing. Now Milo, though, typically when Milo leaps these days, he has learned that he can get farther if he launches at an angle. And so that is something that he typically does these days. He goes at an angle. He ends up further out in the water because in this case he's going after a stick, and he wants to get to the stick as fast as possible, and he can move faster through the air than he can through the water, so he launches himself at a pretty optimal angle. This dog knows himself some physics. And that launching at an angle gets us into the topic of projectile motion in a little bit more detail. That's something we'll talk about in the next set of slides.